Okay, today we're going to talk about a mystery that almost break energy conservation, which was a big thing. So let's study what happened. So this study happened in beta decay. So beta decay, what happened? A neutron, which is inside the nucleus, that decay into proton and electron. The proton stay in the nucleus and the electron goes away. Okay, so what happened was that they looked at the energy spectrum of this electron in beta decay. So if beta decay has two particles, then the energy of electron should be same, a sharp line as seen in this red. But the experimental measurement showed there was a continuous spectrum of electrons energy. The electron came out with also with different angles, which mean that momentum was not being conserved. So sometime high, sometime low, all from identical neutron. The total did not add up. So and the other thing was also wrong, that so if neutrons are going into proton, then neutron is spin half particle, proton is spin half, electron is spin half, and when you combine two spin half particle, you either get 0 or you either get 1. So and the spin angular momentum also looked wrong, and for a short while some physicists seriously consider that maybe energy conservation works everywhere except inside the atom. Maybe nature breaks the rule at very small scale. This was a radical idea because energy conservation is one of the most fundamental processes in physics. Giving it up is like questioning the foundation of the entire field. This Wolfgang Pauli did not like this idea. And one night, after months of frustration, he wrote a letter to a group of nuclear physicists meeting in to begin. He began the letter with very famous line, "Dear radioactive ladies and gentlemen," and he proposed something very bold. He said maybe in a tiny neutral particle also came out of beta decay. It would carry away the missing energy, it would carry away the missing momentum, and it would carry away the missing spin. Because it has no charge and almost no mass, nobody had ever seen it yet. Pauli was also not even sure that this particle was real. He later joked that he had done something terrible. I have postulated a particle that cannot be detected. But this idea worked beautifully. It saved energy conservation, it saved angular momentum conservation, and it made all the numbers fall into place. And a year later, Fermi, so it predicted a particle we now called a neutrino. So a year later, Fermi built a full theory using Pauli particle. He named it neutrino, which means a little neutral one in Latin, and it took 20 years before anyone could have detected one, but Pauli was right. The neutrino existed, and the physics stayed. You didn't have to get rid of the energy conservation, and energy conservation stayed the same. So this was the story of neutrino, how people postulated the idea of neutrino, and then we will talk about in other videos how people actually detected neutrinos. So I hope you like this video. If you do, give the thumbs up, like, share, and subscribe. I will see you next time.